objective is to compare the flatness of a given surface using optical flats. In this experiment, we are going to compare the flatness of any surface with the known flatness, and this known flatness is of our master flat, which is optical flat. And we need equipments in this experiment. One is the monochromatic light source, and another a set of optical flat or a single optical flat of appropriate flatness and size. As you can see from this diagram, this is particularly a light source cabinet which is having a lamp attached to it, and this lamp is generally a low pressure sodium vapor lamp, and it gives almost yellow light. There is a sheet of plastic which is used as a diffuser. The function is to evenly distribute the light over the optical flat and your workpiece to be tested. And you require optical flats. These are circular disc-like objects. They come in different diameters as well as in different thickness. We require only these two equipment in this experiment. And then we have the theory and the diagram. In the theory part, we'll discuss how to measure the flatness of any object or surface. In this case, the flatness of the working surface is tested by comparing its flatness with a master flat of known flatness. So you have an optical flat, which is an optical grade piece of glass, and it can be made of borosilicate glass or quartz glass, and it is highly polished to obtain an extremely flat surface, maybe on one or both the side. That depends upon the cost of the optical flat. If both the sides are perfectly polished and lapped, then this is a very expensive optical flat. And in most of the cases, for cheap measurement, you will have an optical flat of flatness on one side only. And this flatness, you can say, is of the order of tens of nanometer. And the flatness is clearly mentioned on the curved surface of this optical flat. Here, if you can see, this is an optical flat made of quartz glass, and here you see some numbering or imprint. They mention the level of flatness of this master optical flat, and it will have also have an arrow which indicates that which side is flat surface. It's very simple to visualize. And then you require a monochromatic light source. This is the monochromatic light source, and it will have a sodium vapor lamp, or sometimes lasers are also used. That you all know that lasers are monochromatic and coherent beam of light. Lasers as well as metal vapor lamps, which produces the monochromatic light, they are used as a light source. What you do that you take your part and then you keep there on this base, and then you place your optical flat over the surface to be tested. If you are interested in knowing the flatness of this surface, you will take your optical flat, and suppose this top surface is a flat surface of this piece, so you place this surface over the surface to be tested, and then you keep this assembly under the monochromatic light source. You will observe some bands on the surface of this optical flat when you see the surface perpendicular to your eyes. And this particular type of band formation is due to the interference phenomena. Suppose this is a surface which you want to test, and if you place your optical flat over it, and if this surface is having some deviation, so always there will be some air gap formed between these two surfaces. This surface, the optically flat surface, and the surface you want to test. There always be some air gap, and this will be in the shape of a wedge. Suppose this is a monochromatic light source, this is a light ray. It will fall on the surface of this optical flat, and from this surface it transmits to here, and you know that some reflection will take place at this optically flat surface. So this will be a reflected ray coming out by the splitting of this primary, and then some part of this ray will transmit into this air, and it will again reflect at the B point, and it will come out from the surface of this optical flat. And then you see there are two light rays, and these two light rays will have some path difference. So this path difference will be this A to B and B to C. So this is the ABC path difference. And as per the interference principle, if this path difference is equal to the half the wavelength 1 by 2, or if lambda pi 2 is where lambda is the wavelength of the light source, you already know that what type of light you are using. You will have an idea about its wavelength. If this path difference, this length ABC is equal to lambda by 2, odd multiple of this wavelength, then due to this particular path difference, these rays will be in out of phase, and due to the out of phase, there will be a destructive interference. The intensity of both light waves will cancel each other, and you will see these types of dark band at the point B when you are seeing from your eye perpendicular to this direction. You can also use some camera or some image capturing device so that you will have this type of band, and this will be the region of your bright region. Similarly, at point B, E, or on, you will have different types of dark and bright fringes. The distance between two dark band or these two white fringes will be equal to lambda by 2. And this will become a source of the calculation of your flatness. So in this experiment, we'll be interested in knowing this distance or the number of fringes forming on the surface of this optical flat. You will place your eye here and visualize the type of fringe pattern forming on the surface. If you can visualize easily, it's not a problem, and otherwise if you are finding some difficulty in knowing the location of these fringes and how many fringes are formed, then you can also place your some image capturing device here, and then you can see the pattern on any screen or your computer screen. So if the optical flat under test has a really flat surface, means suppose I'm taking an object which is my slip gauge. You all know that the surfaces of slip gauges are very flat, and they also have a very high degree of surface finish. You will find this type of equally spaced straight lines of the fringes. And as I told you, your optical flat will have some degree of flatness. Here you see it is 0.2 micron, and this black arrow is showing which side is your flat side. So this is pointing downward, so this means that this lower surface is your optically flat surface. Basically, the formation of these interference fringes, it determines the flatness of the workpiece surface, and we are comparing with respect to the flatness of your master optical flat, and we'll get the flatness within the fraction of the wavelength of your light used. If your surface is totally flat, it is perfectly flat, then also you will not observe these kind of fringes. So for the fringe pattern formation, there should be some minimum air gap between the optical flat surface and your test surface. If your surface is nearly flat, not perfectly flat, then you will have this type of fringe pattern. So you will have these parallel lines, equispaced parallel lines of dark and bright fringes. And if this test surface deviates from flatness, you will observe these types of curved lines. And now with the help of some small calculation and some visual observation, you can measure the error in the flatness. There is a very simple method. You will take one band which is curved in shape. You will make this vertical line just touching the surface, or try to make it as a tangent to this curved surface, and then you will consider this fringe and try to join the ends of this fringe from here to here. Then you will try to see how many fringes are coming between these two lines. If you observe only one fringe, this bright portion is coming between these two lines. So that means we already know the distance between these two lines is nearly equal to lambda by 2. You will have the flatness error in the range of one fringe, that is lambda by 2. So lambda by 2 means if you know the wavelength of your light source, you can easily measure the error in the flatness. Then after this, what is the procedure? Procedure is very simple. The first thing you have to take care about the cleanliness of the surface. You will sufficiently polish the surface to be tested so that it will reflect enough light. If your surface is not perfectly polished, then it will not reflect the enough amount of light source and there will be a problem in the formation of interference fringes. And then what you will do, you require a monochromatic light source that we already know that it comes in the form of a cabinet. You will switch on your monochromatic light source, and then this sodium vapor lamp, if you have seen in your day-to-day life while walking on the road at night, these sodium vapor lamps, they take some time to acquire proper illumination. You have to switch on the monochromatic light source for some time period. The optical flat is placed on the surface to be tested, and you will gently apply pressure if there is no interference formation. If you are not able to visualize any interference fringe, in most of the cases, if your surface is properly polished and clean, then you don't have to apply any pressure. And sometimes due to the presence of some water or dust, you gently press the surface, and then from that moment you will start observing the interference fringes. And then this monochromatic light source is directed on the flat surface through the optical flat, and you will observe the interference fringe pattern. I told you, if the surface to be tested is perfectly or nearly flat, then you will observe this type of interference fringes. And suppose if your surface is either convex or concave, if it is the case when this is a convex surface, in normal condition you will observe when the lights will fall from here to here, you will observe concentric rings at the surface of this optical flat. Then it will become challenging for you to measure this error in the flatness. So what you will do, from one end you will try to press this optical flat so that it will make a contact here, and then your wedge film will form in this particular region, and then due to this you will have interference fringes in the curved shape. So in the curved shape, now easily you can observe, you can measure the error and the flatness. You will consider, suppose this is the fringe you want to test, you will draw a vertical line and try to join the end of this fringe and this fringe. You will observe how many fringes are coming in these two particular lines. Here you will observe one fringe is here and another fringe is here, so you will have this error of two fringes. Two fringes will become your lambda by 2 plus lambda by 2 equal to lambda. There will be an error of lambda that will be equal to the wavelength of your light source. And similarly here also, here it is not making any contact, so here in the center you will observe these concentric rings, and at the center there will be an illumination as there is no contact, and whatever be the light falling from in this direction, it will be reflected back. So here you will observe a glowing circle at the center. And for that particular case, here you will also press your workpiece at this end so that somewhat an air wedge will form, and basically this smallest impression gives you an idea where the actual contact is occurring between the optical flat and the workpiece. Here in this case, when you are pressing your optical flat from here to here, this end will try to press circle at this particular end. So these patterns you will observe with the calculation of the formation of these two lines. You have to consider any fringe, consider this fringe, try to make a line just touching this fringe, and consider that fringe only, try to join the end of this fringe, then visualize how many fringes are coming between these two lines. The calculation become very simple. And suppose if this line is coming between these two fringes, then 1 lambda by 2 plus lambda by 2 divided by 2, that means lambda by 4. Now the error in the measurement will be lambda by 2 plus lambda by 4. Similarly, you can perform any type of measurement by capturing the image forming on the surface of this optical flat. This is a very simple process method. Before using this optical flat or performing this experiment, your workpiece should be properly polished and it should be clean from dust, dirt or any oil. You can use any organic solvent like acetone so that it will remove all the contaminations present on the surface. Do not slide the optical flat on the surface, as this may cause the scratch on the optical flat, and with the prolonged usage of this optical flat it will become unusable. You don't have to rub your optical flat on the surface to be tested. Just you place your optical flat slowly on the surface to be tested, and then you illuminate the light source over the surface of this optical flat. And the band should be viewed from a distance of at least 10 times the diameter of the optical flat. This is the conventional or a thumb rule to visualize the fringes from the top of the optical flat. You have to maintain at least 10 times the diameter of the optical flat. So you have to maintain this much distance, or if you are not able to visualize it properly, or if you can't make this calculation, then you can use any image capturing device. And the line of vision or this capturing of image must be as nearly perpendicular to the optical flat as possible. These are the precautions you have to take care of. This particular device is widely used in industries where they require a high degree of flatness and precision, and this flatness has very big importance in areas where they require fitment of the parts and assembly. One such case, I had a chance to visit Hindustan Aeronautics Limited. There was a shop called the lapping shop. You know that this type of surface finish is achieved, and what they were doing lapping, and they were doing honing of the parts of different parts of engines and hydraulic pumps. All aircraft parts are very precisely made, and the assembly of the part is a very critical issue. So if there is small clearance gap between the parts which are working together, that clearance can cause a catastrophic failure of the components and lead to the failure of your aircraft. In automobile industries, for engine parts and hydraulic pressure parts where perfect lapping of the surface is required, they are commonly using this equipment for the measurement of a flatness. That was a brief discussion about this topic. So, if you like the video, then please subscribe to my channel, share it with your friends, and don't forget to hit the bell icon for the latest updates. Thanks for watching my videos.